Welcome to the lectures on modern digital communication techniques. So, in the previous lectures, we have been looking at equalization techniques. The earlier set of equalizations that we have seen are single shot equalizer, namely the zero forcing and MMSE equalizer. In both of them, we directly get the equalizer coefficients in one calculation, in one step calculation. Then we put forward the situation where we would like to do it in an adaptive fashion based on the error that we compute when we get the output of the equalizer and compare it with the desired response. So, we have taken a system identification model by which we can estimate the channel coefficients. We have taken an inverse system identification model by which we could find the weight coefficients. If we find the channel coefficients, then we can follow it up with equalization by procedures as mentioned earlier, such as the zero forcing or the MMSE. So, when we say we want to adaptively calculate the channel coefficients, we want to make an iterative approach in which at every step we would like the cost function to be lower than the cost function, that is the mean squared error, less than the previous iteration. So, first we describe the method of steepest descent. It successively adjusts the weights W, that means whatever we have found, to the next iteration in a manner or in the direction of the steepest descent, that is opposite to the slope of this. So, if the slope is in this direction, that means if there is some W, let us say, and this is the cost function. So, if the slope is in this direction, we would like to go in this direction, and if it is a bowl like this. So, if we are here and the slope is in this direction, we would like to come down so that we attain the minimum of the cost function. So, just a note at this point I would like to mention, for a subject like this and the particular course that you are attending in this particular mode, it may not be feasible to go through all the details of such advanced mechanism. However, I am still exposing you to the known or most popular techniques which are used and can be easily accommodated in the receiver. Regarding examination, we will try to ensure that the questions that are usually put forward in evaluating these kind of algorithms, as we are discussing, which is usually very cumbersome, is made in a way that you could address them within the limited time that is possible. And I would highly encourage you to follow the assignments that would be given along with these lectures, so that you practice what the kind of way we can evaluate the understanding of knowledge in this particular area. However, the particular things that we have discussed till the point where we have come up to the maximum likelihood detector at the receiver seems to be a pretty minimum basic requirement to understand this course. So, moving ahead, so let us say we define G as the gradient of J, which is the derivative of J with respect to W. We can define the weights in the next iteration as the weights in the previous iteration and adjust it with some step which is a function of G. So, one has to calculate the slope. Once one calculates the slope, then with a certain step size one would like to continuously improve the weights from one iteration to the next iteration, and in every iteration one could get outputs y n, which would add to the computation of the errors, which would finally drive this particular weight calculation. So, when we apply this method of steepest descent, as we have just described, to the Wiener filters, which we have described earlier, that means we had described Wiener filters which acquires the value in single shot. So, we like to apply this method to the method of Wiener filters. We define E, that is the error, as the desired signal minus the estimated value of desired signal that the filter produces. So, which is the error term, the D is the desired signal, D cap, which is the estimate, is the outcome of the filter, that means the inner product of the filter coefficients and the input to the filter. So, the cost function j in the nth iteration would work out to a expression which appears like this. Again I mentioned we need not worry much about how this expression comes, it is a matter of algebraic computations, and we will not require you to remember this particular expression in the examinations. And then if you calculate the gradient, one would get a simpler expression which is given there. Again I mentioned one need not worry about remembering this expression either. So, as we proceed, we would define the weight in the next step to be the weight in the previous step. So, we put an underline indicating a vector as we had done for signal expansion. So, we follow the similar notation, plus a mu, that is the step factor and gradient of j. So, there is a half. So, half and 2 cancels out, and there is a minus sign earlier, you may have noted that. So, there was a minus and a half, this minus and a half would cancel out this 2, and this minus becomes a plus and this plus becomes a minus, where R is the covariance matrix, we have defined this earlier. Similarly, we have defined P, and these are the weights in the previous iteration. So, what we find is that this calculation is a deterministic gradient, because we are as if calculating this a priori, and it follows on improving in this manner, which requires you to calculate the expectation of the output with respect to itself. So, there is a covariance matrix to be calculated in order to calculate this particular, or in order to use this particular method. That means, you need to have the prior PDFs of the output of the signal. So, that means of the channel response. The other method which is followed comes from the family of stochastic gradient. We call it stochastic gradient because it does not use a deterministic gradient, and it does not need one to calculate the cross correlation and the autocorrelation matrices. So, we have the output y n, which is the inner product of the input and filter coefficients, and the error as the desired signal minus the output. So, we have been shifting between y n and d cap of n, this is the same thing. The filter taps in the next iteration is the filter tap in the prior iteration plus the mu, that is the step size, times the input and the error which we have computed here. So, in these kind of functions we do not need to calculate the covariance matrices, we just need to calculate the error, and what we can see is that the rate at which this changes is varying randomly, because we have a random input sequence and the error which is a function of the previously learnt weight values. This relaxes some of the conditions. So, there are convergence issues, but if we can design the input sequence appropriately, we could find the weights to converge pretty fast. These kind of algorithms are also very commonly used for estimation of channel coefficients as well as for estimation of equalizer coefficients. So, next, once we have found methods to find the channel coefficients as well as covered the underlying philosophy of channel equalization, while maintaining that the received signal, the overall transfer function of the received signal after getting processed follows a raised cosine pulse shape, we are now interested in studying some more non-ideal characteristics, which is the estimation of carrier phase and clock. So, till this point we had assumed perfect synchronization of the carriers between the transmitter and receiver, as well as perfect synchronization of the clock from the transmitter and the receiver. That means, we assumed that there is no phase distortion, there is no error in the sampling clock instants, and so on and so forth. So, when we look at this whole set of operations, what we essentially do is we are estimating some of the important parameters of the communication system. So, when we write the received signal, it is R of t is equal to S of t plus noise, and S of t is the S L of t e to the power of j 2 pi f c t and the real part of that. At the receiver, when we demodulate, we do the correlation receiver or the matched filter receiver. In both the cases, we generally take the projection of the signal on the basis functions. So, projection on the basis function means you integrate from 0 to t times f k of t, which is the basis function, and r of t. So, that means multiply r t with f k t, integrate from 0 to t. If your basis function, if it is a PAM, your basis function is cos 2 pi f c t times g of t minus n t. If it is QAM, you have a cosine and you have a sine. If it is Emery f s k, you have e to the power of j 2 pi m delta f t. So, most of the cases you have a sinusoid or a cosinusoid getting multiplied by the received signal. Now, this we have assumed to be 2 pi f c t, that is f c is the carrier, and the transmitted signal also had 2 pi f c t. However, it is not necessary that the received oscillator has the same frequency f c, and there could also be a phase difference between the transmitted signal and the received signal. Further, the clock which runs at the receiver, which is used to sample at time instants capital T, may not be perfect, and it may not sample at exact t instants, nor does the receiver know which is that particular instant of time where it should sample. Although the receiver can keep on sampling at regular capital T intervals, but when to start is not known at the receiver. This is because of propagation delay and unknown clock start and the oscillator start at the receiver. So, when we try to estimate these parameters, it is very helpful that we look at the general class of estimation theory, using which we should be able to formulate a few expressions. The expressions would be used directly where we apply the signal model which we have developed so far, and once we apply the signal model into the expression of the estimator that we will see shortly, we will be able to estimate the parameters of our interest. So, we have the general problem of estimating the signal, and we would like to state the mathematical estimation problem, and as we have stated since the beginning, we want to write down the expression of the signal at every stage of operation, so that we get an unambiguous output which could be used by the designer or the implementer of the particular communication system. So, we can state it as the mathematical problem, and let us see what it gives us. So, in determining good estimators, that means we want to get good estimates. Just a small note, we already have discussed the channel estimation procedure and signal estimation, where we have done channel equalization. Channel equalization is as good as estimating the signal. So, we did not mention the estimation detection philosophies there, but here we would like to describe them with a little more time, so that you get the basics of the philosophy which is used in deriving the estimators. Once we get those expressions, they will be helping us in getting estimations of carrier phase and clock. So, in determining good estimators, the first step is to mathematically model the data. Once again, if we are not writing the appropriate expression of the data, we will not be able to write the algorithm. We want to operate on the data. So, since data is inherently random, we use the PDF to describe the data, because a random variable is well described by its probability density function. Typically, the probability density function is parameterized by the unknown parameter theta. That means, we have p indicating the PDF of the observed data, and there is some unknown parameter theta. It will be clear shortly what we mean by this particular description. So, suppose our PDF is Gaussian, again which is very familiar to us because we have Gaussian noise. So, we receive a particular sample, that sample contains a data point as well as there is noise. So, the conditional PDF of the observed signal conditioned on a particular data is the Gaussian distribution with the mean value of that of the signal. So, the PDF of the data can be expressed in this form, where theta is the mean and x 0, I say x 0 because we have a single observation. So, this PDF can be plotted along the x 0. So, we put x 0 and we parameterize this by different values of theta. So, what we find that if I have received x of 0, which is negative on this side, most likely value of theta would be theta 1 and not theta 2 and theta 3, right. And this kind of description we have given when we talked about the maximum likelihood detector, and we have used the PDF and we have used some form of philosophy of the estimation detection theory, which will be apparent very soon. So, what we see from this is theta influences the PDF of x. So, for example, if this is d, this is 3 d, this is minus d, all we mean to say, if I receive x 0 somewhere here, the most likely function or the most likely signal that must have been sent is minus d, which is represented as theta 1 over here. So, the likelihood of that parameter being theta 3 is much less, because if we take the PDF, the area under the curve here is much less than the area under the curve over here. So, we could plot like this, that theta, that is the parameter, causes x. That means, we have chosen minus d to be transmitted, and that would influence what I observe. Of course, theta is perturbed by noise to produce x. What we want to do, we observed x, we want to infer what theta was. So, this is an inference problem, that is what we are interested in, the reverse direction, that is what we are going. So, if we see this picture, we will find that specification of the PDF is very critical in determining a good estimator. That means, if we do not choose the appropriate PDF, or the PDF itself affects the choice of estimation, right. And in practice, we are not given the PDF, but must choose one that is consistent with the data. What it means is that in practical systems, it is hardly possible to have the exact PDF of the signal. So, we generally choose a PDF which closely matches that of the data, that is all that it means. And the other important criteria we should have is that it is mathematically tractable, otherwise we will not be able to derive the algorithms. So, when we have a estimator, we would like to evaluate the performance of the estimator. Some of the questions which we ask is how close the estimated output will be that to the original parameter that we want to design, that we want to estimate, and are there better estimators available. So, before we proceed, we must remember that the estimator is a random variable, right. This is a very important concept, because the estimator is some function of the received signals. The received signals are random, therefore, the function also should produce a random outcome, and therefore, we can say that this function represents a random variable, which is the estimator, and hence its performance is described statistically by its probability density function. since the estimator is a random variable, we use PDF to describe its behavior. And we should also note that use of computer simulations to assess the estimator performance is never conclusive. So, we should try to find the PDF, and there are other techniques by which we could estimate whether these two are achieved or not. So, one way to do that is to find whether the estimator is unbiased, that means on an average it produces the parameter which we require, and whether it produces the minimum variance. So, we should be able to analytically describe these behaviors of the random variable of interest. And then we have the minimum variance unbiased estimator, as just stated. Unbiased means on an average the estimator or the random variable reaches the parameter to be identified, and it is minimum variance, that means no other estimator is found whose variance is lesser than that of what we have found. So, some of the procedures to determine the minimum variance unbiased estimator are through the Cramer-Rao lower bound, which we will see shortly, and through the Rao-Blackwell-Lehman-Scheffé theorem, or with linearity constraint. We will restrict ourselves to this, and then we will move to the maximum likelihood estimator. Just a few note before we are actually able to produce the estimator is that if we consider PDFs with two different variances, one with 1/3, another with 1, this is just for representative sake. What we can make an observation is that the smaller the variance, that means tighter the PDF, better is the estimator accuracy, because if the PDF is spread larger, we cover a larger region in this axis. So, it is less accurate, that is what we can say. So, for example, of course, we call this as the likelihood function, as we have mentioned before, and we would like to consider the x 0, that is the observed variable, and this is the PDF parameterized by the unknown parameter along with the observed data. So, I have the PDF function, which is let us say this, I have observed this, I will put this here, and A is to be estimated, which is given as theta over here. So, what happens if I consider this particular PDF, which is parameterized by theta, and suppose I have observed x at this point. So, when I put the value of x in this PDF, right, I could find, so of course, this PDF is parameterized by a or theta over here, I would find that this function yields a value which is here. So, this tells the likelihood of receiving x 0 when I put into this PDF for a choice of a or theta, as it may be. If we consider this dashed PDF, which is green in color, then we will find the likelihood to get the signal is almost 0, which is very small. So, this is the shifted PDF, right, whereas the black one is nearly at its mean. Now, if we compare the one with this red PDF, which has a larger variance, right, what we find is the likelihood would be more than that of the green, but it is significantly less than that of the black. So, all what we try to mean is that the estimator accuracy, the more accurate estimator will be the one which has a lower variance, and as well as it is parameterized by the unknown parameter theta. So, our job would be to find the parameter using the likelihood function, and this description also explains why shall we call the PDF when it uses the data set and the unknown parameter as the likelihood function. So, that picture is drawn here, it is a bigger version of the picture. So, that visibility is there, and of course, we have if sigma 1 squared is less than sigma 2 squared, that means as sigma decreases it becomes smaller, the curvature increases. So, it becomes sharper and sharper, and the sharper it is, the better is the estimator, that is what we stated, and these points are the likelihood values of x 0 driven by these different PDFs noted in different colors. So, what we see that estimator accuracy is somewhat related to the curvature. So, we will discuss more about or tell you about the curvatures. Once again, whatever we are discussing at this instant of time are for sake of information. However, the final results that we get will be the ones that are important and the ones which you may remember. However, if you are interested in designing receivers, one should learn these methods. However, from an examination point of view, one need not exactly remember all the detailed steps of derivation. So, instead of taking the likelihood function directly, we consider the log likelihood function. The reason to take log likelihood function is when we take the log, the expression becomes easier, because instead of exponent we get it directly here, and we take the derivative. So, what we have, so for the Gaussian PDF what we say is when we take the double derivative over here, we see that this particular expression is inversely related to the variance. That means, we can conclude that somehow curvature could be connected to this parameter. So, we define that the curvature in general as the negative of expectation of this particular function. We will see how it plays an important role. Next, we define the very important Cramer-Rao lower bound. So, in this it is assumed that the PDF p of x theta, x is the observed, is the parameter to be observed, to be found out, satisfies the regularity condition. So, that means, the first derivative of the log likelihood function and the expectation of it goes to 0, right, where the expectation is taken with respect to the PDF this. Then we can state that if this condition is satisfied, the variance of any unbiased estimator, which we have described before, must satisfy the condition that the variance is bounded by this, which is the curvature. That means, the lower bound of an unbiased estimator is given by the Cramer-Rao lower bound through this expectation, through this expression, where E is the expectation used computed using p of x theta. So, where the derivative is evaluated at the true value of theta. So, this is calculated at exact value of theta, because we want to calculate the variance for a certain value of theta. For instance, if this is theta and this is the variance of the estimator, we would like to calculate at a particular value of theta what is this. So, then we can calculate the variance of the estimator. So, what it says is that if this condition is satisfied, then the variance of any unbiased estimator is lower bounded by this expression. Furthermore, it also states a very important thing, that an unbiased estimator may be found. So, it not only tells the lower bound of the estimator, it also gives an opportunity to find the unbiased estimator if and only if the derivative of the log likelihood function can be factored into I of theta. That means, it has to be factored in such a way that there is some function I of theta and g of x minus theta. G is some function which has only the observed data minus theta. So, if you can factor the first derivative of the log likelihood function, in that case you could claim that the estimator is given by this function g of x, and it is the MVU, that is the minimum variance unbiased estimator, while the variance of this theta is equal to 1 upon I theta, and I theta is nothing but this expression, right. So, that means, it tells you that if one can factor it in this form, one would always find the estimator given by this. So, it is very simple to understand that it is a function of observed data. This function produces theta cap, which estimates theta, and the variance is set equal to this, that means it achieves the lower bound, right. Just to summarize, so an estimator which is unbiased and attains the Cramer-Rao lower bound is said to be an efficient estimator, because you can find the estimator directly, and on an average it will produce theta, while the variance is the minimum lower bound. So, it will be unbiased as well as it will be lower bound, and therefore, you call it the efficient estimator. So, what the Cramer-Rao lower bound gives us is the lower bound of any estimator if the regularity condition is satisfied, and if you can factor the first derivative of the log likelihood function, you can directly get the MBOE estimator. Thank you.